Electrochemistry. When we start talking about electrochemistry, it's important that we talk about, solution chemistry, and it's helpful to pay attention to exactly what the species are present in the reaction of a mixture. Things like solid, liquid, gas, aqueous solution. And particularly in an aqueous solution is to think about the ions that are present. This is going to be most important. Ions. Okay? What ions are present, right? So, to understand reactivity, we have to be aware of what is changing, because if something's reacting, obviously it's going to be changing into something else, one compound to a different. So let's talk about the different types of equations that we can represent a chemical reaction with. The first one would be a molecular equation. And this lists the reactants and products in what's called their molecular form. So for an ionic compound in solution, even if these ions were to break up in solution, when we're writing the molecular form, we keep them together as a compound. In an ionic equation, we're going to show all of the strong electrolytes, those are the strong acids, strong bases, and soluble ionic compounds, as being dissociated into their ions. So this is where we show that silver nitrate as breaking into the silver ion and the nitrate ion, the potassium chloride into the potassium ion and the chloride ion, because that silver chloride is not soluble. We keep that together because it is a solid. And then the potassium nitrate, potassium as an ion, that's dissociates, so it's drawn that way. So keep in mind particle diagrams too. Excuse me, while we're doing these. Alright, now the net ionic, if you remember, it's been maybe a little while, is when you cross out any species that does not change from the left side to the right side of the equation. These would be the spectators. So in the equation shown, we see that nitrate is on this side as an aqueous ion, and it's on this side, so those get crossed off. Same with the potassium. They don't enter into the actual reaction, which is the silver ion reacting with the chloride ion to form that precipitate sodium chloride. Not sodium chloride, silver chloride. Okay, and as mentioned earlier, the things that don't change, the things that are still staying as ions in solution, are called spectators. So writing net ionic, write a balanced molecular equation first, dissociate all of the strong electrolytes, strong acids, strong bases, soluble ionic compounds, cross out anything that remains unchanged from the left side to the right side of the equation, and then write the net ionic equation with any species that remain. So you should be able to write molecular equations, ionic equations, and net ionic equations, and know the difference between those three. So neutralization reactions. Hopefully you're familiar with these. An acid and a base react to form a salt and water, an ionic compound and water. This would be a molecular equation with acetic acid reacting with sodium hydroxide to form sodium acetate and water. That, hopefully you remember that, oh, wait a minute, going back here. This is a weak acid, strong base. I don't know why I felt I had to do that, but strong acid reacting with the strong base. The net ionic equation. Here's the molecular. Here's the ionic. You notice the chloride ion and the sodium ion are spectator. So for a strong acid, strong base, a neutralization always is written like this. For a strong acid and a strong base, it's always the hydronium ion plus the hydroxide forming water. Let's talk about oxidation-reduction reactions, and this is all the basis of electrochemistry. Oxidation occurs when an atom or an ion loses electrons. reduction occurs when an atom or ion gains electrons. And when we have an oxidation-reduction reaction, we have to have both of those occurring. Whatever is losing its electron, being oxidized, has to have a species that is gaining an electron, being reduced. There are two mnemonics to remember oxidation reduction. The first one is oil rig. Oxidation is losing electrons, reduction is gaining. The other one is Leo says Ger. Losing electrons is oxidation. Gaining, this should be an E, I spelled it wrong, sorry. Gaining electrons is reduction. I use oil rig, so I generally screw up. Leo says Ger. Okay, but two ways to remember. So, how do we determine whether a redox reaction has happened or not? Well, we have to assign oxidation numbers to each element in a neutral compound or a charged entity. These are not actual charges for the most part. They are just ways of kind of keeping track of where the electrons go by seeing what the assigned charges are. So, elements in their elemental form always have an oxidation number of 0. Oxidation number of a monatomic ion is the same as its charge. So like a sodium ion would have a oxidation number as +1. Nonmetals tend to have negative oxidation numbers, although some are positive when they are combined with certain elements or ions. Oxygen has an oxidation number of -2, except in the peroxide ion. The peroxide ion is not one that we generally use, but it is an O2 with a -2 charge. That is the peroxide ion. Each oxygen in that peroxide ion would be assigned an oxidation number of -1. Hydrogen is -1 when bonded to a metal and +1 when bonded to a nonmetal. We don't talk a whole lot about metal hydrides, so this concept is probably new. We are very much used to hydrogen being a +1, but it is assigned an oxidation number of -1 when it is bonded to a metal. Nonmetals tend to have negative oxidation numbers, although some can be positive in certain compounds or ions. Specifically, what comes to mind is sulfur, chlorine, and nitrogen. Fluorine, being the most electronegative, always has an oxidation number of -1. Other halogens typically have an oxidation of -1. However, they can have positive oxidation numbers, most notably in the oxyanions. You may go, what's an oxyanion? It would be something like the chlorate ion, chlorate being ClO3-. In this case, each oxygen is -2. Let me change colors here. Each oxygen, I'm just going to do this real quick. Each oxygen is -2. I have 3 of them, so it's a total -6. Overall, this ion has to have a -1 charge, so that means the chloride has to be a +5. Okay, and that's going to be a little weird probably for some of you. The sum of the oxidation numbers in a neutral compound is 0. The sum of the oxidation numbers in a polyatomic ion is the charge of the ion. Okay, so displacement reactions, also known as single replacement. They oxidize an element. The ions then are reduced. I'll put up the little videos separately. And so if we look at this reaction here, I've got copper metal and silver ions reacting to form the copper ion and the silver metal. The reverse reaction doesn't happen though. Okay, and let's go back here for just a second. If we assign oxidation numbers, copper in its elemental state is a 0. This silver is a +1 because it's just the ion charge. This copper ion is +2. Silver in its elemental is 0. So this copper is losing electrons to become a +1. So this copper metal is being oxidized. Silver is gaining an electron. It is being reduced. If you notice, the oxidation number is also being reduced from +1 to 0, which is really where the name comes from. Alright, so displacement reactions. They only happen spontaneously in one direction, and that goes back to this activity series. Okay. We will pick up with this in the next, I think. Oh, let's keep going. Sorry. Electrochemical reactions. Electrons are transferred from one to the other. Okay, we assign them oxidation numbers to keep track of what's losing and gaining. Right. As mentioned, oxidized when it loses electrons. It's reduced when it gains electrons. Here's something that is just a memorization thing. What is being reduced is called the oxidizing agent. So the hydronium ion oxidizes zinc by taking electrons from it. What is oxidized is known as the reducing agent. So zinc reduces hydrogen, the hydronium ion, by giving it electrons. That's just memorizing things. We looked at the examples in class.